Section 3.4, proofs with perpendicular lines. So the first thing here we need to know is the distance from a point to a line. So if you have a line here and you have a point, maybe point A, and we are trying to measure the shortest path from A to the line. Think about it. If you were standing here at point A and we were going to have a race, first person to run across this line wins some prize. Which direction would you run to try to cross the line first? Well, you'd probably want to run the shortest direction, which you could run to this corner. You could run, let's call that corner B. You could run to this corner, C. But you see, the distance from A to C is a lot longer than from A to B. So the person running this route is probably going to do worse than the person running this route. But if you think before the race starts, you want to run the shortest distance. It's going to be this distance right about there to point D. That's the shortest way. And when you measure distance from a point to a line, you always measure the shortest distance. So you would find the distance from A to D in this case, because A to D is perpendicular and the perpendicular line is going to be the fastest one to get there. Then you would use the distance formula from chapter 1. Next vocab word, the perpendicular bisector. The perpendicular bisector, if you have a line segment, perpendicular means 90 degrees. Bisector means it's going through the middle. 90 degrees. Going through the middle means the two pieces are congruent. So this would be the perpendicular bisector. Perpendicular, 90 degrees. Bisector means it's going through the middle. The next one, if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So let's say we have two lines, and angle 1 and angle 2 are congruent. Now we also know that angle 1 and angle 2 are a linear pair, that they make a line. The line is right here, right? So what do you know about two angles that make a line? Well, a line is 180 degrees. So 180 degrees, except angle 1 and angle 2 have to be the same. So if they are the same, then the measure of angle 1 is equal to 90 degrees, and the measure of angle 2 is equal to 90 degrees, which means if this is a right angle and this is a right angle, then they are perpendicular. Because the two angles have to be 90 degrees. And that is called the linear pair perpendicular theorem because it talks about linear pairs with a perpendicular line. The next one is the perpendicular transversal theorem. So in this one we have two lines that are parallel. We'll put the parallel symbols there. Maybe call them line A and line B. And then we have a transversal. And the transversal is perpendicular to only line A. Let's call that line C. Then C is also perpendicular to line B. But this really makes sense if you think about the other things we've learned. This angle is 90 degrees. A and B are parallel, so that means that this angle, which corresponds to the 90 degrees, would also have to be 90 degrees. Because corresponding angles are congruent, they both have to be 90, which means these lines down here are perpendicular also. The next one, the lines perpendicular to a transversal theorem. Very, very similar idea. But here it is. It's kind of backwards. Here it says if two lines are perpendicular to the same transversal. So A and B are both perpendicular to C, then A is parallel to B. But again, this makes a lot of sense because if these are perpendicular, then this is 90 and this is 90. So the corresponding angles are both 90. If the corresponding angles are both 90, then by the corresponding angle converse, the lines must be parallel. So these theorems right here, they're useful. They make life faster if you know them, but you can still get around it using the basic theorems and converses that we learned in section 3.2 and 3.3. Not necessary. Makes it faster though. All right, example 1. Determine which lines, if any, must be parallel and explain your reasoning. So, in this picture, A, we know P and S are perpendicular, and that's all we know. No parallel symbols, no other perpendicular symbols. Does this mean any of them are parallel? Well, the only option would be P and Q. If we knew that Q had a 90-degree angle, then the answer would be yes. But here, there's not enough info. And the reasoning is that we know nothing about Q. Okay, picture example B. Let's look at this first. Look, we have two lines and a transversal. The top angle and the top angle are both perpendicular. They're both 90 degrees. So that means that these two lines have to be parallel. P is parallel to Q. Now the way I talked about it, saying the corresponding angles are both 90 degrees, they're congruent, I would say that they're parallel by the corresponding angle converse. You could just as well say they are parallel by the lines perpendicular to a transversal theorem. To me, that's a bit of a mouthful. I would go with the CA converse. What about R and S? All right, there is R and S with one transversal. We know this one's 90 degrees, but we don't know anything about those angles up there. If we look at the other side, here's our transversal. We know this one's 90, but we know nothing about those. We can't tell anything about R and S. Only P and Q because of the corresponding angles. All right, let's look at C. All right, so I don't know, let's work with M and N first. There are two transversals. We could look at the top transversal, in which case we don't know anything about these over here, so that doesn't work. If we look at just the bottom transversal, hey, we do kind of know something here. Now, they're not as they are marked right now. They don't match up. They're not corresponding. They're not alternate interior. They're not alternate exterior. They're nothing. But using the idea that this one is 90 degrees, and here we have a linear pair, they make a line. What that means is that this one must be 90 degrees also. And now we have corresponding angles that are congruent. That means M is parallel to N by the corresponding angle converse. Technically what we used the linear pair perpendicular theorem to say if one's 90, the other's 90. And then we used the lines perpendicular to a transversal theorem and said, hey, look, if they're both 90 degrees, then the lines are parallel. Corresponding angle converse is just fine. Now what about J and K? So let's look at maybe just J and K with this one transversal. The same sort of thing is going on. This top right angle is 90 degrees, which means the bottom right angle also must be 90 degrees, because 90 plus 90 equals 180. And now the bottom right and the bottom right are both 90 degrees. They're both right angles, which means J is parallel to K by the CA converse. Now, there's one more example here, and this is not on your notes. You're going to have to write this one down, but this is one you would expect to see on the homework, so I want to talk about it. It's about the distance again. It's this picture right here, distance from a point to a line. So you're going to see problems like this. Find the distance from point A to line BD. And then they're going to give you some points, A, B, C, and D. What you need to do is use the distance formula. So distance, you could look it up. You could use the formula sheet, which is posted on the class resource page. Distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. You're going to plug points in and just calculate the distance. The catch is we need to know which points to use. So we're trying to go from A to the line. So we should probably use point A, which is 5, 6.75. Now this is not drawn to scale, so please don't pay too much attention to that, but 5.675. 5, 6.75. Now we do need another point, so the question is, do we use B and calculate this length? Do we use C and calculate this length? Or do we use D and calculate this length? Well, remember, you're always calculating the shortest length, and what you'll see in the picture is a 90-degree mark. The 90-degree mark is the one that's going to tell you which way to go. And if you don't see it, it's the shortest line. This dashed line is going to be the shortest way. So we're going to use A and we're going to use C. And these are the points we're going to use. So x1, y1, x2, y2, and we're going to plug them in. So square root of x2 minus x1, 2 minus 5, squared, plus y2 minus y1, 3 minus 6.75, squared. 2 minus 5 is negative 3 squared, plus 3 minus 6.75 is negative 3.75, and we're squaring that. Negative 3 times negative 3 is 9. And don't forget your big square root symbol the entire way down. Negative 3.75 times negative 3.75 is approximately 14.1. It's positive because a negative times a negative is a positive. 14.1 plus 9 is 23.1. So the square root of 23.1 is approximately 4.8. So this is all something that we've done before. The only difference is that now you have to pick which points A, B, C, or D you use in the distance formula. After that, it's just using the scale that you've previously learned. And with this, you should have enough information to do your homework for section 3.4.